Hey students, in this video we're going to talk about derivatives and what the graphs tell us. So it's a two-parter. We have a second derivative test in another video. So in part one of this section, we're going to talk about what the graph of the first derivative tells us. Um, the first derivative is going to be able to tell you where a function is increasing or decreasing. Remember, the derivative is the rate of change of the function. And so if we're looking at the graph of the derivative, which again is the rate of change, where the derivative is positive is going to mean that our rate of change is going to mean our rate of change is positive, which means that our original function values should increase on that interval. When the graph of the derivative is negative, is going to mean our rate of change is negative, which means our function value should decrease on that interval. So when we look at this, we have this graph. The red graph is a parabola, and the gray graph, the line, is its derivative. And if we're looking at the gray graph, where the gray graph is above the x-axis, which is from -1 to infinity, we notice that if we trace from left to right, our function is going up where the gray graph is positive. If we continue tracing from left to right from where the gray graph is below the x-axis, our original graph is going down. And so that's what the first derivative tells us. It tells us whether original functions either increasing or decreasing. And it also can tell us where we have relative extrema, like a local maximum or a local minimum. Analytically, we can do this using the first derivative test. And the first derivative test, we have to we have to find the derivative. We have to find all of our critical values and place those critical values on a number line. And then we make a sign chart using that number line. If an interval is positive, it's going to mean that the function is increasing on that interval. If the interval is negative, it's going to mean that the original function is decreasing. And if we switch from positive to negative on our sign chart and the original function is defined at that value, we have a local maximum. If our sign chart changes from negative to positive at a critical value and the original function is defined at that critical value, we have a local minimum. So analytically, this is there's a lot of algebra. There's only one step of calculus that we do, and that's finding the derivative. So our first derivative, for example, a is f prime of x is 10x to the fourth minus 20x cubed minus 30x squared. We want to first find our critical values. We set this equal to 0. We factor out our greatest common factor of 10x squared. That's going to give us x squared minus 2x minus 3 equals 0. And this continues to factor to be x minus 3 and x plus 1 equals 0. And we get 10x squared. So if we have 10x squared equal to 0, we'll get x squared equals 0. So x equals plus and minus 0. So just 0. And we also get x minus 3 equals 0. So x equals 3. And we also get x plus 1 equals 0. So x equals -1. So our three critical values are 0, 3, and -1. Over here, let's put 10x squared. We're going to put x minus 3, and we're going to put x plus 1. And I'm going to draw a number line, we'll say right here. We'll put a number line. Oh, how did I mess up on a ruler? Drawing a straight line. So we'll put our number line right here. And so on your number line, you should put your critical values in order. So our smallest critical value is -1. The next one is 0, and the next one is 3. And on either end of the number line, we're going to put negative infinity and positive infinity. So the way I do my first derivative test is we need test values on each interval. So something between negative infinity and -1, we could use x equals -2. So you could substitute this value into the derivative and record the sign. It is a lot easier if you just consider the product of the signs of the factors. So here, like if x is -2, 10x squared is going to be positive, x minus 3 is going to be negative, and x plus 1 is also going to be negative. So when I multiply those three numbers, I get a positive. We don't care what the number is. We just care that it's going to be positive. Now, for this example, I'll show you exactly what we're doing. So if x is actually -2, -2 squared is 4. 4 times 10 is 40. So what we're really multiplying is 40 times -2 minus 1 is -5. I'm sorry, -2 minus 3 is -5. And then -2 plus 1 is -1. And so that would give us 200. But we don't actually care that the value is 200. We care that the value is positive because it's going to tell us on this entire interval our derivative is positive. So here we're just going to do a positive, a negative, and a negative, and that equaled a positive. So that means that we are increasing on an interval. If something between -1 and 0, I would use, I don't know, x equals -0.5. Then if x is, we'll put a line here. So if x is -0.5, then 10x squared is positive. All right, let me write this better so it's in line. So if we have x equals -0.5, 10x squared is still going to be positive. X minus 3 is going to still be negative, and x plus 1 is going to be positive. So when you multiply those three things, you get a negative, not a positive. We would get a negative value. So we're going to have a positive times a negative times a positive, which is negative. So that means that we are decreasing on this interval. If we choose a value like x equals 1 for the interval 0 to 3, so then at x equals 1, 10x squared is positive, x minus 3 is negative, and x plus 1 is positive, we also get a negative. So we're going to have a positive times a negative times a positive equals a negative. So also decreasing on that interval. And last, on this interval 3 to infinity, if we choose x equals 4, then we'll get a positive, and a positive, which multiply gives a positive. So we have a positive times a positive times a positive, which equals a positive value, which is increasing. So what we can summarize from our derivative is that f of x is increasing on the intervals -infinity to -1 union 3 to infinity, and f of x is decreasing on the interval -1 to 0 union 0 to 3. All right, so notice we split our interval at 0. That's because at 0, the function has this cessation of motion, but then it continues the rate of change is zero there, so it cannot be decreasing or increasing. So we have -1 to 0, and then 0 to 3, even though the function is continuous at x equals 0. Um, so that's where the function is increasing and decreasing. And then we have, we can identify the maximum and minimum. So f of x has a maximum at, so where our sign chart changes from increasing to decreasing is where we have our maximum. That happens at -1, and the y coordinate that is associated with that, we'll just put f of -1 for right now. What you would just substitute -1 back into the original function. And the value is not super important. It's just how we would get it. And so then f of x has a minimum at, so where our sign chart changes from decreasing to increasing. So that's going to be at the point 3 f of 3. Oh, so for both of these, we should say local. So you'll see this called a local or relative, but it's the same thing. So both of these, to get these values, you go back to the original function. And notice at x equals 0, our other critical value, nothing happened. And so we'll just make a note. It is not necessary for a critical value to be a max or a min. It just doesn't have to happen. All right, so I'm gonna skip this example with tangent inverse, and we're gonna move to this one where we have to do the quotient rule. So this will be the last example for this video. So we want to identify where x squared over x squared plus 1 is increasing, decreasing, and possibly identify any critical values. I think this might get spicier if we change this to -1. Nah, we'll leave it alone. So let's see. So f prime of x is going to be our low function, which is x squared plus 1 times the derivative of our numerator, which is 2x, then minus the numerator times the derivative of the denominator, which is 2x, and we divide all of that by x squared plus 1 squared. Simplifying, we would get 2x cubed plus 2x minus 2x cubed, all divided by x squared plus 1 squared. And so that obviously simplifies to be just 2x over x squared plus 1 squared. Now remember, a fraction equals 0 where the numerator equals 0. So 2x equals 0 implies x equals 0. And then we worry about x squared plus 1. So when you've done the quotient rule, you don't care about the square. You care about what's internal to the square being 0. So x squared plus 1 equals 0. We would get x squared equals -1. No real solution here. No real solution. So if we make our sign chart, let's see if I can draw a straight line. I did it. So then on our sign chart, we'll just put our lone critical value of x equals 0. So, and remember, we want to use the factored version of 2x and x squared plus 1 squared. Choose some value less than 0. I don't know. We'll say -1. So if we use x equals -1, we would have in the numerator, that value would be negative, and we would divide by anything squared is going to be positive. So that end result is a negative, which means that we're decreasing on that interval. And then from 0 to infinity, we would have, I don't know, x equals 1. And we would then, I don't know, so then we substitute in 1, you would have a positive 2 divided by 2 squared, which is also going to be positive. So that is a positive, and that's going to be increasing. So here we would say f of x is increasing from, what is it? 0 to infinity, and decreasing from dyslexia caught up with me, from negative infinity to 0. All right, so let's double check our work. Our derivative is the low function times the numerator minus the numerator times the derivative of the bottom. So that's 2x squared plus 2x minus 2x cubed. Yeah, everything works out. So, and then we have f of x has a local, so here we have only a local minimum at 0 f of 0, which actually turns out to be 0 because 0 squared divided by 0 squared plus 1 is 0. Cool. So this is our video on what the graphs of derivatives tell us. You know what, actually, you can stay around if you want to. We're going to just look at the graph of this function and get some more information from it. Otherwise, I'll see you in class, but stay on with me if you want to. So let's type this function in Desmos. It was x squared divided by x squared plus 1. And so notice, oh, we'll turn this on too. Nope. All right, so that's the part that we want. So I'll turn this off, turn this on. So the red portion of the graph corresponds to where the dotted red line corresponds to the original function. The solid red line is the graph of the derivative. So notice for the red line, the solid red line is below the x-axis, which means that our function should be decreasing. And we can see that that's true if we zoom out. The values are decreasing all the way from negative infinity to 0. And then at 0, for the solid black line, that's the graph of the derivative again. And it's increasing. It's positive, which means that our original function is increasing. So again, this is what the graphs of derivatives tell us. And we can clearly see we have a minimum value at 0. All right, thanks for watching.